So all I care about is what are the A of n's when I take this thing. These are the equivalent of writing down my frequency content for the Fourier transform, except these aren't frequency contents anymore. They're just some functions that you're representing in, and that will give you the strength, and that generically is what always costs you order n squared to get. Okay, yeah. I will write it down. It's actually here in the notes. Let me write it down over here. I ran out of space there, but the inner product is there's a weighting. They are orthogonal with respect to the square root of 1 minus x squared. So here, what you get is C0 is 2. All the other Cn are 1. And this is a Dirac delta function, which is 1 if n is equal to m and 0 otherwise. So I'll have two different functions, t0, t1. This is always going to be 0. So anytime you take two different n's, it's going to be 0. But then if you take n equals 1 and 1, then it's going to give me a weighting. In other words, it's going to mean the length of the function, as it were. Okay? So this is your orthogonality relationship for these polynomials. Okay. By the way, come back to here. Normally we associate this process with doing some kind of order n squared operation to get all these coefficients. But here's the thing to notice. See how we defined everything here? Everything is defined in terms of this cosine theta or cosine n theta. Cosine n theta, wait a minute. Isn't that your basis set for a discrete cosine transform? It is, right? So when you have a FFT, it's the e to the I omegas, x's or t's. And then you have cosine and sine. It's either sine or cosine of things like this. So in other words, one way to think about it is, wait a minute, these functions through a transformation can be related to a cosine transform. And how quickly can I compute that cosine transform? N log n. So in other words, you actually don't do order n squared because of this connection to the dct, this discrete cosine transform. You can get the calculation then down to n log n. Okay? That's the big deal. That's why we're talking about Chebychev today. We would not even mention Chebychev if n log n wasn't there. It would just be some abstract, some guy from Russia, whatever, who wrote down some functions I don't care about. No, but because it's n log n, now you care about it. Or maybe you still don't, but I'm going to try to convince you that you should care. Okay? That's my job. Am I convincing you? How am I doing? Victor, are you convinced? No, Victor's sold. He's first row. That's how you work your way up to the first row. You get convinced easily like that, and you're like, yeah. You guys in the back don't have much hope? I don't know. All right, so let's talk about boundaries then. And the boundaries are going to hopefully start becoming somewhat obvious by what we're trying to do here, because you've got cosines floating around. Okay? And so, let me erase this. So here's the big deal. Here's your connection. This is the big formula associated with Chebychev, is this. The x equals cosine theta. And if I have this here, I can do the way I defined Chebychev, I can do the discrete Fourier transform. But here's the connection formula, where theta basically, right, is going to go from 0 to pi. So when theta is 0, cosine 0 is 1. When theta is pi, cosine pi is negative 1. Right? So this is the connection formula, which x going from negative 1 to 1 corresponds to theta going from 0 to pi. Okay? So now let's take a generic function, f of x. And now I want to represent this in terms of Well, x is equal to cosine theta, so there we go. So this is some now function of theta, if you want to think of it that way. What I want to do is now take the derivative, dg d theta. Okay? So take the derivative of this thing. Well, if you're taking the theta derivative, here's how the chain rule is going to work. It's taking f prime times what's inside. Derivative of cosine theta is negative sine theta, right? So you get negative f prime times sine theta. Now here's the thing to observe. What happens with this derivative at 0 and at pi, the two endpoints? Sine of 0 is? Sine of pi is? Awesome. So what are my boundary conditions? 0 for the derivative. Sweet. So the derivatives, boundaries, give this to be 0, and what you have is no flux. Okay? So that is the way you think about using these boundaries. It's like, okay, at the boundaries, I have no flux boundary conditions. That's what's imposed. Okay. So let me make a few comments about how to calculate things. So we have now the boundary condition. We have the functions we're going to use. So let's go through some details now about using this function. So first of all, we are going to do expansions of this form. F of x is equal to a of n t of nx, n equals 0 to all the way to whatever, infinity. Of course, we're going to cut it off at some capital N. But there we go. That's the typical expansion. And the question is, how do I calculate the coefficients? Well, to calculate coefficients, what you do is you multiply both sides by t of mx and 1 over square root of 1 minus x squared, and then take the inner product. And we're going to use orthogonality. And if you use the orthogonality conditions that I wrote over there, you find that a of k are equal to negative 1 to 1 there it is. So you project. This is just like the Fourier transform, but my kernel now is this stuff. It's not e to the I. It's just that function times this divided by this 1 over 1 minus kx squared. Just a different kernel, but it's just like a Fourier transform. Okay? We felt more comfortable with Fourier transform because it looked nice. E to the I, very simple looking thing. Here, it's a little more complicated, but no different. Okay? This is what you're going to get out, and now you're going to have a function of the k's. Again, the k's are going to play a role now, which is as you integrate over all of x, this is going to be a function of k. Okay? And remember before in Fourier transforms, we had an intuition about what the k's represented. K's represented frequencies. Here, k's, what do they represent? Well, they represent which one of these modes I'm working with. Okay? All right. So there's that. Now, there are some properties I go through in the notes about this t of n's. Page 183. No, sorry. Your notes is a different page number. But right below where I show this formula, there are a set of properties associated with this. And I'm not going to write them down. But you should, you can just peruse them at your leisure. Okay? But the most important thing I want to highlight to you is this, which is we are solving this thing on a domain but really, I'm on x is negative 1 to 1, but really I want to make use of that cosine theta, don't I? Because that is how easy it is to define things. You do everything in terms of cosine theta. So really what I want to work with is the theta variable. Okay? So there's a connection between x and the thetas.